My name is Simone Vannuccini. I'm a new, relatively new, now it's 1 year old, Chaire, the Professeur Junior, which is a new position here at the Université Côte in economics of artificial intelligence and innovation. And today, I don't know if you have ever seen the movie Arrival, where the aliens come and we need to learn to talk to them. So today, I'm a little bit like the alien, but I'm trying to convey how economists would think about innovation totale, which is actually a very interesting concept that was introduced in this, by Marina in this workshop, in this series of events. So first of all, I want to thank Marina, Virginia, and Marion for the invitation. You're very lucky to have this team here teaching you, because they're very nice. Economists sometimes are a bit annoying, so you might see today. But let's get started. So so the idea is that to give you an economist perspective on this idea of what I would say is a combination of a series of concepts that we have in economics to understand these technologies. Now, as I'm a bit scholastic, there are 2 readings, if you want, and if you have a QR code, you can scan and find the papers. These are, and also for self-reference, are 2 readings of mine. But the idea is that there are a couple of references that you can look at. I guess the second one is not downloadable, so you can ask me then, but I wanted to put a QR code because it was fancier. Now, one is about artificial intelligence, and one is about, in general, radical and transformative innovation. So, I'm starting from a very broad framework of what do we know as economic scholars about technology and innovation, okay? Because what we usually try to do is to identify some commonalities between the technologies, because once you have learned that some technologies are characterized by certain features, then you can try to find these features in other technologies. If you want that response to the very broad question that we can ask today, is artificial intelligence or is quantum something really new? Or at the essence, at the foundations, they are not so new, so that when, for example, we talk about standards as the very interesting talk that we had before, then we know that we can follow certain paths. When we talk about regulation, we know that maybe we do not have to reinvent the wheel every single time. So what do we know at a very high level of abstraction? First of all, technologies and innovations. Not all innovations are technological, but we focus on technological innovations. Am I talking too fast? Are you okay with that? Okay. So not all technological innovations are alike. So there are some you will see that impact the society, the economy, industrial structure more than others. Some intervenes on cost structure, some intervenes on things that we can do. Second point, the forces that shape innovation, so what induces economic actors to innovate, and the mechanisms that innovations put in place tend to be always the same. It has to be about demand, it has to be about technological feasibility, it has to be about scale, might be related to entry barriers in a new market, about technological complexity, but the things are always the same. Just what matters or what changes is the weight that these different factors play. So if I want to start to innovate in textile, or I want to start to innovate in quantum, for example, the complexity of the knowledge behind is different, hence this element will play a major role as a barrier or as a push toward innovation. Third point is that we know that most of technological breakthroughs, so if you want, the innovation totale, so the more radical, more transformative technologies, I will be more precise later on though, they tend to create new industries, they tend to create new markets. And then these markets, not always, but often tend to follow certain patterns in their evolution. these patterns are usually called the industry life cycle. For example, take the automotive industry. Behind there is a radical innovation, which is the car engine. So you didn't need horses anymore. So the industry starts in 1896 in Germany and the US. In the first 20 years, in the US, there were 300 car producers. A lot of small companies, they try many variants of the product. Then there is what is called a shake-up, or it's a sudden drop in the amount of the firms, and then you have a stabilization. So if you look, for example, at quantum today, if you look at AI today, so the story, we will discuss that later on, but the story of OpenAI and Anthropic and the story of all the startups in AI is that you have a big turbulence, big entry in the market, and then you have consolidation at a certain point. So what is the Microsoft attempt with OpenAI was to have a hidden merger and acquisition, in a sense, even though the structure of the agreement was relatively complex. So I always bring this quote from Halvarian, who is now is the chief economist of Google, but before he was a famous economist, talking about IT, so digital technologies, not current technological changes, but he said, like, if you want to understand information technology, the economics behind, it's always the same. The building blocks are always the same. What matters is the ways in which these are recombined, okay? So in this talk, I'm going to introduce some concepts that hopefully will help us to place this idea of the total innovations in perspective. And then I will talk more about artificial intelligence because it is my field of expertise. However, I would say that in many cases it applies also to quantum. But here, I mean, if you want to talk quantum, you talk to Virginia, who is the la crème de la crème, as they say in France, about quantum. So, so then you can talk to me more about, well, actually you can talk to Marina about artificial intelligence, so you don't have to talk to me. But if you want, you can. So, first of all, first step, how does an economist think? In general about innovation. So if I want to have an economic analysis of technological innovation, I have to think, to put in line at least 3 elements. One is can I measure, or can I assess the willingness to engage in the creation of new knowledge? The willingness means the balance between the incentives and the constraints. So what pushes me as an economic actor to introduce something new, and what refrains me from doing something new, okay? This willingness might be of different kind. Might be technological willingness, so that's why I call it technological opportunities. So, for example, the field of quantum is quantum theory is relatively old. The field of quantum technology is relatively new, or some of the subfields. So, technological opportunities are still wide. Think about another technology, which is something I've been working on, which is semiconductors, or microchips, okay? So I don't know if you ever heard the concept of the Moore law. Have you ever heard about this idea? So the Moore law, layperson definition is the fact that microchips they double their processing power, compute power every 18 months or 2 years. In practice is that we were able to cram more and more transistors on a little silicon wafer, so to double them. This leads to an exponential trend in performance. And why I'm saying that, because in semiconductors, from the 50s to nowadays, there was a lot of technological opportunities. So you could improve the technology that's okay. You could improve the technology very much. So that incentivized you to invest in the technology. These technological opportunities could be internal or external. So you could have your R&D, research and development department inside the firm, but that requires scale, or you could buy solutions, and that's, you have corporate governance issues, you have startup issues, you have a third-party collaboration, you have academia and private firm relationships. And the other side, of course, of the incentives and constraints are the economic chances, or the economic-related things. So, yes, to build a rocket that goes to space or to place satellites on low Earth orbit maybe is feasible, but is it economically viable? So if I start a startup today, will I make money? Because a lot of things are feasible. So if you look at if you look at patents, not standards, but patents, so brevets, there are a lot of inventions. So these are inventions. If you look at innovations, which is inventions that go to the market, that are much fewer. Okay, so a lot of things we know, few things is economically viable. And you might want to have profits, yes, so you go for an innovation, or you might want to gain market power. So if you think about Uber, if you think about other companies that invest in digital technologies, they also want profits. But actually, none of the digital tech companies are making profits. They make revenues, but the cost of the revenues is higher than the revenue. So what they want is to conquer the market, because when they are dominant, then they can make profits. So you have to look at that. You have to look at another thing that economists always think about, and maybe lawyers too, which is trade-offs. I don't know if you know what a trade-off is, but a trade-off is some dimension over which you have to take a decision. Either you do more of something, then you have to do less of something else. So you cannot pursue all the quantum technological trajectory at one time. Okay? You have to choose where to go, because you have a trade-off in the budget that you allocate. So if you have $1 million, in how many boxes it's like playing, let's say, at the casino. I mean, you have to allocate your money in certain boxes, and you cannot do it, I mean, unless you have infinite resources. But if you have infinite resources, that's not anymore an economic problem, because economic problems are problems of scarcity. So how do we allocate resources? Okay. You also need to know who are the actors. Are they public actors? Are they private actors? Are they public and private connection? Are they networks? Are they consortia? Are they large firms? Are they small firms? Are they vertically integrated firms like car producers? Are they specialized producers? And so on and so forth. And then you need to know the features of these actors. Do they have complex knowledge? Do they have patents? Do they publish? Do their founders started companies before in other sectors, so they are spin-offs or scale-ups of other companies. So that's how an economist would think. I hope you don't mind if I sip a glass of water. Are you still with me? Good. So now I wanted to go to brag what economists do. They use graphs. So but I'll go very quick into that, because I don't want to tell you formulas. This is why I cut all the formulas. The idea is that what an economist would do, she or he, would try to abstract once again on what I told you, to try to see whether these general ideas, they fit different technologies. So for example, this is on the left you have a graph that summarizes the most basic analytical model on how we try to think about how much firms should invest in research and development. Okay? So here you have on the on the x-axis you have R, which is investment in R&D. €1, €2, €1 million of euros, 10 million of euros, etc. On the y-axis you have pi, which is profits or returns, C, which is cost, and small pi, which is, I'll tell you in a second, net profits. So when I told you about technological opportunities, the idea, for example, is that you could figure out, you could estimate this larger curve here, this pi of R, is what we call a return curve. So for each amount R that you spend in R&D, which profits do you expect to make? Okay. Now this curve has a specific shape, so it goes always up, but a little bit. Well, it's called a concave curve mathematically, but it doesn't matter. Because the idea is that in every, and that's an economic concept, in every effort that an economic actor do, there are what are called decreasing marginal returns, meaning that the next effort will give you always positive but smaller returns. So if you invest €0 in R&D and you invest from 0 to 1, that's a big gain. So that's it might bring to nothing because it's still is a probabilistic kind of thing. So you might be unsuccessful depending on where you search. But from 0 to nothing is a big jump. From 0 to nothing is no jump. From 0 to 1 is a big jump. From 1 to 1,000 is a big jump. But from 1 million to 1,000,001 euro is not a big jump. So if you would increase your expenditure in R&D from 0 to 1 to 2 to 10 to 100 euros, then if you would measure the change in this curve, which mathematically would be the derivative of that, so the change is positive, but the second derivative, so the speed of that is decreasing. So you will always gain less and less and less and less. Now assume that you have a cost to do R&D, meaning that I need to hire people, or I need to build a factory, or I need to buy equipment, okay? And imagine, it can be different, but imagine that the cost is linear. So, for example, if R&D are R&D scientists, like you would work in a department, in a lab, then my cost as a company owner is the salary that I pay to you. But if I hire one of you, your salary is the cost. If I hire two of you, it's 2 times your salary, and then it's 3 times your salary. So the cost is linear, okay? So it just grows depending on the number of people that you do. So what I want to say with that is that if you want to look at the incentive for innovation is not to invest as much as you can in research and development. Because at a certain point, the third curve is the difference between the profit that you obtain in investing in R&D and the cost. And this net profit, so the profit that you obtain from innovation, for example, embedding the innovation in products and services and selling them on the market, and the cost that you have in that, at a certain point, the costs become larger because the gains, they cannot grow continuously in an exponential way. So what happens is that you conceptually, this is this pi r without the tilde on top is the subtraction in any point of this larger curve and this cost curve. Okay? So if you subtract any point, you have this stuff. Now, if you look at now what economists usually do, this is a function. You find the maximum of the function. What is the maximum of the function? The peak of the mountain. So you find, so you can find it technically, but what matters is that this point here would be the top, the peak of these returns. So that corresponds to the amount of R&D that gives you the maximum possible profits of your innovation. So that's how we think. Now, in the real world, that's much more complicated. So you do not have any of these curves. This curve is a fuzzy thing because you cannot know if you invest in R&D, you obtain profits. But maybe nobody wants your product. Maybe your costs are exponential because, or even not a function because you need to build the factory and hire the people and finding them. Maybe there are no skills. So everything is more complicated. But what I wanted to tell you is that these stories applies to everything. The first curve is a measure of technological opportunity. If it is higher, means that's an industry where it's easier to obtain profits out of innovation. If it is lower, means that there are, for each R&D, less gain. So a sector where there is less opportunity. And the cost might be that you have a cost that is more steep or less steep, depending on the industry. Now, you can do a lot of very interesting experiments here. For example, here, I just made an example in which I lowered so you have this gross profit, as we call this pi tilde 1, and then I lowered the pi tilde 2 by a certain share. So I lowered the curve. Imagine that the amount of the curve goes down depends on the fact that the investment that you do to come up with an innovation, it's stolen by a competitor. So you do an effort, you research, and then you have somebody copying you. So somebody copying you, what does it mean? It means that for every amount of R&D that you do, somebody is stealing the knowledge that you look for. But if somebody steals your knowledge, then for each unit of R&D, the profit that you obtain is less because you have less control of the market. Hence, the net profits is lower. So if there is an imitator that lowers your gross profits for a given amount of cost, you will do less R&D. Now, if you are a lawyer, what does this imply? It implies that you might want patents, or you might want intellectual property right protection. In this case, I'm not saying that you want them all the time. But in this case, if you have a patent, intellectual property right, what does it do? A patent is a contract that tells, I tell you the result of my search of knowledge, you can use it, but you pay me a fee, or you don't use it, because if you do, I sue you. So either you are a monopolist because the others cannot use your idea, or you become a monopolist because the other pay you to use the idea. So what a patent would do would lift that curve back and would make you invest more. Okay? Now, once again, I tell you this for a very specific thing, and I hope I still have time, because that will come back usefully later when we talk about radical innovations. Now, this is how we think. Then you can make this more complex, more dynamic. You can have strategic interaction between firms. But that's a story that applies always. Okay? So for example, if you make that model dynamic, so with more time or time periods, then maybe my investment can be used by others, and I can use the investment of the others, so you might not want to have a patent. So the decision whether to have intellectual property rights might depend on the specific setting you're talking about. But that's a general setup of the problem. Now, this for innovation in general. When we talk about innovation totale, then you have different concepts in the literature. For example, one concept is the one of radical innovation. So people use them interchangeably, this concept, but they're not the same. So a radical innovation is literally defined from the technical viewpoint. So it's an innovation that changes, so that introduces new functions, so you can do new things, and also changes the way in which existing things were done. But you have alternatives. So for example, if you have a very little or very slow change in what the technology does, and the way in which its components are organized, this is called an incremental innovation. It's just a small improvement, okay? So a microchip with 10 transistors and with 11 would be an incremental innovation. You also have architectural innovations. Architectural innovation is, they happen when function remains the same, but the components of the technology. So think about a fan. You know, a fan, you can have a fan here to make fresh air next to me, or I can take it, unbundle it, put it on the ceiling, so the components are organized differently, but the function is always the same, to move a bit of the air. So that's an architectural innovation. You can have modular innovation when you add new things. So for example, if you would be old as I am, but not so old, at a certain, the first mobile phone that I bought, which was a Sony Ericsson, had a little camera that you could plug into the phone. So the phone was still doing the same things. The components were the same. But on top, you could add an add-on. So that was a new module, the photo camera. Or think about a drone, okay? Unfortunately, you can have a drone. It's a technology with certain component, does some stuff, it flies. But then you can add, I don't know, a sensor. It's a modular innovation, a camera, a bomb, unfortunately, some arm that picks something. So that's modular innovation. Or then you have, when you have a new technology that does something new in a very different way, then you have a radical innovation. So for example, artificial intelligence is software that makes predictions based on data using a new logic. So that's a new function because it's automation of predictions based on a new logic which is inductively extracting pattern from data. Hence, technologically, possibly a radical innovation. But there are other concepts. I don't know if you ever heard about this story of long waves. So many innovations, they have broad impacts on the economy. So the steam engine is not just a technology that creates force by processing steam. If you attach it to a car, you have the automobile revolution. If you attach it to a boat, you have literally the trade revolution, because before steam engine on boats, trade was limited on the seasonality of winds. So you could trade in one direction from US to Europe and the other direction based on when the wind was blowing. You remove that constraint, once again, incentive and constraints, you have a societal profound transformation. And this is captured by the idea of long waves. I didn't tell you before, but I don't know if you ever, because in law sometimes that is have you ever heard the name of Joseph Schumpeter? So Schumpeter was this guy, an economist, that an Austrian guy that is the one, somehow the first suggesting that innovation might disturb the equilibrium in the economy, okay? So but he had this idea that looking at Austrian firms, that innovation comes in small entrepreneurial firms. Then he went to US and he found out that even shoe factories and pin factories, they have large R&D departments. So it's like, okay, then innovation comes from large firms. And then, well, actually what he said is both. But then people then started to debate on that. That's why my field of study is actually called neo-Schumpeterian, because we debate endlessly these kind of things. But then, so Schumpeter introduced this thing. Schumpeter was also a weird guy. He wrote the first book is the theory of economic development. The second is deeply political also. It's called Capitalism, Socialism, and Democracy, where he was comparing, say, planned investment in innovation. He also said that he wanted to be the best horse rider, the best economist, and the best lover of Austria. And he was already 2 out of 3, but he wouldn't say which. But if you Google his photo, I doubt he was the best lover of Austria, because he looks like Master Yoda, but that's not important. Anyway, so why do I mention Schumpeter? Because Schumpeter thought was building on an idea introduced even before by Nikolai Kondratiev, who was a Russian economist, that suggested that economic systems, they evolve along broad cycles. Okay, you might have heard in high school, these are the first industrial revolution, the second industrial revolution. Okay, so these broad cycles that he called long waves, he captured statistically, was one of the first doing that statistically in the 20s. He did not say that it's innovation, but that opened up a whole world of people studying how technologies kickstart that. Okay, and Kondratiev then ended up in a camp, not a vacation camp, but a Soviet camp, because if you were in Soviet Russia saying that the economy goes back and forth, you go against the idea that, I mean, the rate of profit of capitalism should be ending at a certain point. Hence, there was not a very good for him to suggest this idea, but it's good for us to think about that, because then economists of technology started to elaborate how certain technologies might produce worldwide implication, which is then what Marina called the innovation totale. So the idea is that you have a nested set of mechanisms in which you introduce a radical innovation, so an innovation that introduces new functions in a new way. This innovation is not in the void. So if you have a computer, for example, a laptop, or if you have a car, these are all technology systems. So they are collection of technology. So here there is a screen, there is a hard drive, there is a semiconductor chip device, there is a graphical card, etc. And all of these are radical innovation, but they are combined together. So they have ties that take them together. Okay? And each of them evolve. So you could have still a computer with a solid state memory, as they have now, or with an older memory. The computer would just be slower, but it still would work. Or you can have the same computer with a LED screen or a non-LED screen. So or with a Pentium processor or an ARM processor. So all these technologies are radical. They all have what are called their technological trajectories. So they evolve along their path of evolution. But they're also kept together by the fact that they are tied in systems. When you have a radical innovation, this usually breaks the ties of this system. So if you have you introduce you introduce the fuel combustion engine, then this changes the way in which cars work. This changes the labor market for, horse drivers. This introduces the need to have gas stations. This changes the trade once again. So you have this, the more the innovation is radical, the more it disrupts existing systems, the more it have broad changes. And if the innovation is very radical, it creates what are called technological revolutions. Okay? So it changes many systems. And when these technological revolutions, they change the whole society, they change what they are called the techno-economic paradigm, so the world in which we're in. Super example, so the easiest example. So your parents did not know what internet was. I started to use internet maybe, let's say, early 2000s. But the society pre and after internet, or pre and after information and communication technology, is very different. Okay, so the whole societal envelope in which we think about how we interact, how we work, how we start a business, that has changed because of the whole techno-economic paradigm changing. And this has been represented by economists in a very stylized way. This, for example, is from a work of a very good economist, Carlotta Perez, that then me and a co-author, we copied, but we build upon. And she had this idea that all the technological revolutions, they follow broadly a similar scheme, okay? When they arrive, and then they have a phase of eruption when nobody cares about them, but they are there. Then there's a phase of frenzy in which people start to get super excited about them. But then this leads to speculation. Speculation leads to a collapse of the companies that use this technology. And then the pieces are collected by companies that instead of speculating, they are building on that. So if you think about, you were very young, but if you know what was the dot-com bubble, it was a bubble of IT companies at the turn of the century, or turn of the millennia then, because everybody invested so much in IT, but then there were no applications. So the IT technologies, a lot of frenzy, collapse, and then we have now the IT infrastructure with the tech giants, etc. So if you look at the laser, if you look at the steam engine, if you look at the electric dynamo, they tend to follow this pattern. Now, the question could be, is AI the same? Is quantum the same? Here, I'm not telling that it's a deterministic thing. It's not going to happen like that. But it might follow these steps, so better to know. Now, here I listed all these technological revolutions. I will send you the slides. I will share the slides so you can look at them, but you can identify different technologies. Different phases of driven by certain radical technologies. Now, there are other concepts. One that you hear always is that of disruptive innovation. So you must be disruptive, move fast and break things, as Mark Zuckerberg would say, and that did not work out very well. Not for him, it worked out well. For the society, it worked out a little less well. So disruptive, everybody wants to be disrupt, disrupt, blah, blah, blah. Disruptive innovation is a very specific concept. Disruptive innovation are those technologies that challenge the industrial leadership. So in 2007, when I had the BlackBerry, and I don't know if you know anymore what the BlackBerry was, the BlackBerry was far superior to iPhone 1, okay? It just lacked one thing. It lacked the touch screen. Okay? So what happens is that the iPhone became a disruptive innovation because it was, at the time, technologically inferior, but appealing to a niche technology that the leaders could not pursue because leaders usually in what is called, oh, no, I know, you don't see what I see. Good. The leaders, they usually they follow what is called the innovator dilemma. They had success doing something, so they need to continue to do what made them successful. But then when the entrants come, the entrants might kick their rear part, let's say. So that's what is a disruptive innovation. It is an innovation that comes from the very bottom of the market in a niche, sometimes less good than the established ones, but it makes its way up to the market by conquering demand and conquering consumers. So not a radical innovation is not necessarily disruptive. So if a radical innovation is introduced, diffused, developed by industrial leaders, it doesn't disrupt the market. This leads then to the point that we discussed in the round table, most likely about the role of so you know the tech giants, they are doing a lot of mergers and acquisitions, openly or closedly, like so clearly or just like OpenAI once again. So that's exactly the attempt, one of the strategies that firms have to avoid the innovator dilemma, so to try to calm down potential disruptive innovation and appropriate them. I will tell you even more. You, for sure, know as lawyers, you know what is a killer acquisition? Have you ever heard about that? So in pharma, you acquire companies to turn off their innovations because you don't want to be disrupted. Okay? But that's that's a strategy, product-level concept rather than a technological concept. So they are not the same. And there is even another concept that, sorry, it's the one of general purpose technologies. I don't know if you ever heard about that. But general purpose technologies are those radical innovations that are used in many industries. So think about a laser, okay? So a laser, it can be used in automated cash machines. It can be used as a DVD reader. It can be used to measure stuff. It can be used to shoot people. It can be used to blind your friends with a little laser in the and so on and so forth. So it's the medical industry, the military industry, the retail industry, they all use this technology. So these are technologies that apply to different sectors. Semiconductors, that's a picture from the original paper of 1995 to show you that 1995 is not so long ago, but people were making pictures with ASCII characters instead of generative AI. Semiconductors, you have them in hearing aids, in radios, in computers, in scanners for the medical industries. And these are interesting technologies for a very specific reason. And I go toward the end. Do you remember the problem that I told you before? Don't look at the formulas, okay? So we said, okay, a firm has to decide R&D or the level of technology, here is called T, but that's the same story, based on their technological opportunities, their profits, and their costs. But general purpose technologies usually are technologies that are used in innovation in other industries that innovate. For example, a chip is used by the computer industry to do better computers. So what is happening is that innovation total, like general purpose technologies, they will not face this easy problem like, okay, I have my returns, I have my costs, how much I should invest in R&D. Because my returns here, imagine I produce computers, depends on how good the chips are. Okay? So I need to buy chips to make better computer. But the chips producers, they need to have demand from the computer producers. So what happens is that computer producers, I have these economic problems. But the chip producers have this economic problem, which is the same, but the two problems are connected. So the better computer I do, the more chips I buy. The more chips I buy, the more the chip maker can make better chips. The better chip, the more it is sold to different industries, the more industries will buy. Positive loop. Great. Innovation total, they generate looping positive feedback dynamic. There is a problem here, though, for the radical innovations. Imagine that the industries do not adopt chips. If I don't adopt a chip, then the chip producers, they will not improve, they will not innovate. If they don't innovate, their quality is very low, so nobody will adopt them. If nobody will adopt them, the quality actually will worsen. If the quality worsens, even less will adopt. So you have that innovation total, they might introduce new functions, they might disrupt or might not disrupt market, but they might end up in generating negative feedbacks, dynamics in innovation incentives. That's where policy come in. You know what is public procurement? Public procurement is the government that buys or subsidizes technologies. Think about, so that's not a general purpose technology, but think about solar panels. So solar panels 20 years ago, nobody wanted them because they were very inefficient. So what do? You give subsidies to the solar panel producers because instead of having private demand, they have public demand. With the public demand, they can invest in R&D, lower their costs, make them better, so that then they start to appeal to technologies. So general purpose technologies introduce non-linear dynamics in innovation. When you have a technology that applies to many sectors, it might lead to a long wave of transformations, as we said, a technological revolution, or it might lead to failure of adoption. Now, to conclude, even though I had the full set of slides about AI, but very quick. The point is that, does AI fit into this story? So why I introduced you that? Because first of all, indeed, that's the economic framework to think about these technologies. The second point is what is AI then? Not what you heard about what is AI the whole week. But AI has features of radical innovation because it introduced new ways of doing things. It has also features potentially of techno-economic paradigm because it's transforming many business models, applications, sectors, and so on and so forth. It has the features of a general purpose technology because it is applied in different sectors and inducing innovation in those sectors that uses it. And potentially, but only potentially, is also disruptive because if you are an AI startup, or if you're a quantum startup or a quantum company, you might challenge existing leadership. So if you use this concept, you can have a grid to try to apply to new technologies. And the last word is the following. That's not, even at 39 minutes, so I still have a minute, 30 seconds. That's not enough for AI. That's why I gave you the first reading. Because AI is becoming even a more complex case in which you have that the very technology is becoming industrialized, meaning is more and more produced by private actors. So you have evidence that the private, they play an increasing role. That could be good for size of investment, but could be bad for the narrowing of research and the openness of the technology. You have a whole industry that is building on around AI, given that is affecting in a, let's say, pervasive way the economy. But these effects are not only startupping, new ventures, specialization in the industry. No, it's also hiring people in developing countries to tag the data, so to have a supply chain of data processing that is exploitative of people. And the very last thing is that this is all summarized by one concept, which is a fifth concept that I tell you, which is the one of what is called technological convergence, which is the idea that when you have radical, disruptive, and general purpose innovations, they tend to spawn off new industries, okay, new markets. And if you look in the past, each time that you have, I don't know, new radical changes, like, I don't know, metal cutting technologies, or computing, or chemical engineering, you had new markets emerging. Design firms, process control firms, ICT spawn off the knowledge-intensive business services. AI is doing the same. You have specialized data analytics companies. You have database integration with large language models. So this we have seen in the last 100 years, and this we are seeing with AI. So AI is a new technology, is possibly radical, potentially might spur a long wave of transformation as all the innovation total, but the changes is introduced in the economy is not so new, and what I find always fascinating by the economics approach to that is that we can put the things in perspective so that you can skim the hype away and focus on the key things that, that happen in this technological field. There is also regulation, but I will not talk about that. That's just the summary. So I hope I was able to give you this guided tour of how my brain is shaped when thinking about technologies. And, well, we can talk more about that, but if you have questions, you know where to find me digitally and also physically. So thanks for your attention, for not falling asleep. And, yeah, question open, I think, if you have time, but otherwise, I'm around. And thanks again for organizing this.